In this synthesis example, we're provided with a target molecule containing a sulfide or thioether functional group, and we're asked to provide a synthesis from propene where any reagents that add carbons to the compound contain 2 or fewer carbon atoms. See what you can do, remembering that partial credit is better than no credit at all. In analyzing our target compound, we're looking for the presence of propene in that material. And so if we remember, propene is our 3-carbon alkene. Normally we'd have a number designator for where the double bond is, but it can't help but be between the middle carbon and one of the end carbons in a molecule as small as propene. And there are a couple of places we could conceivably have propene. So we could simply pick the first 3 carbons in our chain. That would, however, require the formation of 2 new carbon-carbon bonds. To pick these 2 carbons, the end methyl groups and the carbons they're connected to, would result in only 1 new carbon-carbon bond, which means a simpler synthesis. That does mean we'd need that to attach to a 2-carbon system. We're told again that any reagents that add carbon atoms have to contain 2 or fewer, and so we would then need that to connect to the sulfur and have the 2 carbons from the sulfur being an extra connection. We could start there and think about adding or creating that sulfide, because we only really have one realistic means of doing so, which is to use the sulfide anion, and we could pair it off with a sodium or something, and we would need to start with the rest of the molecule with a good leaving group present, like a Br, for example, or a tosylate or whatever. That tells us now that we know at least we can get the sulfur connected with its ethyl group, but we need to assemble this other part of the molecule and make this new carbon-carbon bond. Making new carbon-carbon bonds, of course, suggests the use of an organometallic, and we'll note in this case that we want to connect to a carbon that's not the same carbon as one that contains a functional group, but rather is adjacent to it. And that should suggest the use of an epoxide as the most viable route. It's not the only way we could do it, but it would be the most efficient. And specifically, if we think about our carbon-carbon bond coupling step, we would want to use that epoxide, and we would want to follow it up with H3O+. That would give us our 2 green carbons with the functional group at the end, and we would want our 3-carbon system with the organometallic reactive carbon being in the middle. So for example, cyclopropyl lithium. That would give us our carbon framework that we want for the next step. The only thing that we would need to do then is to convert that alcohol functional group into the alkyl bromide or a tosylate. And if we just say we wanted to use a tosylate for variety's sake, we could certainly do that by using tosyl chloride. That would give us an OTS. So a tosylate or a sulfonic ester is also a good leaving group. We could also at this stage just stick with our PBr3 and make the alkyl bromide. Either one of those routes will be perfectly acceptable. To make the organolithium compounds, we want an alkyl halide, like a chloride, for example. We can make the alkyl chloride simply by doing the Markovnikov addition of HCl across that alkene bond. So again, in this case, we had to make several new connections, including a new carbon-carbon bond, as well as a carbon-sulfur connection. We can think about those in either order, but sometimes it's easier to do the last step first. And to get the sulfur and a CH2 group on, we're just doing a substitution with the corresponding anion with a good leaving group, which could have been a tosylate or a bromide, whichever we felt like using at the time. We then made that from the epoxide because we wanted that functional group to be one carbon away from the carbon that was the point of attachment to the organometallic. Which again requires the use of an epoxide with the organometallic, which we made in 2 steps from our alkene.